What makes up most of the cosmos? Not stars or planets or even atoms. It's something scientists call dark energy, and so far, no one has a good handle on what it actually is. Dark energy, first discovered in 1998, is an enigmatic pressure pushing the universe apart at an ever faster clip. Scientists suspect it began flexing its muscles about 5 billion years ago. Beyond that, we know very little. Learning more about dark energy is one of the primary reasons NASA has built the Nancy Grace Roman Space Telescope, a new observatory whose measurements will help us home in on this mysterious cosmic component. Without a better understanding of dark energy, our knowledge of the past and future evolution of the universe is incomplete. Roman will tackle the dark energy problem using different yet complementary methods. A key part of this is a measurement called redshift. Because space itself is expanding, the farther we look, the faster galaxies are moving away from us. This predictably stretches an object's light into longer wavelengths, which translates to redder colors. This redshift indicates how fast the expanding universe is carrying galaxies away from us. By comparing galaxies' speed with their distance, astronomers can see how the universe's expansion rate has changed over time. That could reveal whether and how dark energy strength has evolved. One of these alternative methods is by using exploding stars called Type 1a supernovas. These blasts are caused by the total destruction of a white dwarf star, and each one emits similar amounts of light. But the farther away they are, the fainter the explosions look. By measuring how bright the Type 1a supernovas appear to be, we have an independent way to measure their distances. It was by comparing supernovas' redshifts with their apparent brightness that astronomers discovered dark energy. These studies show that explosions at high redshifts were dimmer than they should have been in any model where the expansion of the universe was not speeding up. Roman will study tens of thousands of explosions, reaching to even greater distances to measure dark energy's influence over time. A quirk of the early universe provides another way to pin down dark energy. For most of its first 500,000 years, the universe consisted of hot, dense, expanding fluid. Small density changes in the fluid excited sound waves that traveled throughout it. Although the waves, called Baryonic Acoustic Oscillations, eventually ceased, astronomers have observed their faint imprint in the way that galaxies cluster together. This provides another way to measure galaxy distances. The Roman Space Telescope will measure how this imprint changes over cosmic history, allowing astronomers to map the expansion of the universe in more detail and probe dark energy's effects over time. Finally, Roman will use a phenomenon called weak gravitational lensing to study how the universe's vast web of matter has evolved under the influence of both gravity and dark energy. As light from distant galaxies travels across billions of light years, its path is subtly bent or lensed as it passes through gravitational wells surrounding matter along the way, both normal matter and the mysterious dark matter we can't directly detect. This warping slightly distorts the apparent shapes of galaxies. By measuring these tiny changes over millions of galaxies, Roman will create detailed maps of matter's distribution throughout the cosmos. Tracking how cosmic structures have grown over time reveals how dark energy influences the universe's accelerated expansion. With each technique cross-checking the others, Roman surveys will peer deeply into dark energy, providing important data to help scientists figure out what exactly it is, and how it will determine the ultimate fate of the universe.